You remember in the last class we looked at the propagation of unoriented string. Well, in the last class or the previous one we looked at open string exchange. The one loop diagrams for open strings, which had a problem when you thought of it. Had a problem, you could interpret that problem by thinking of it as being exchange of closed strings from one source to the other. The problem arose because we were exchanging things without momentum. If we had momentum here, we would have sum over 1 over ki squared plus mi squared, and we get some number. But since we didn't have the momentum here, we just had this 1 over mi squared. And when m went to 0, that was a problem. Okay, we got a divergence. Okay, the divergence happened because massless fields, namely in this case the dilaton, couples to the source that is created by having open strings, and that gave rise to this dilaton tadpole that we didn't know how to. I mean, that gave us a problem. Now, in the last class, we started looking at unoriented strings. Okay, we started looking at strings such that omega, the parity reversal operation, was a gate symmetry on it. And you remember that we also had to take into account also these Klein bottle diagrams. So we had to put the projectors 1 plus omega by 2 inside the trace, and that gave another source for this object. And you remember that we found that the relative sources were like n squared. That came from the open strings. We were assuming they were Chan-Paton factors. N squared by 2 to the power d plus 2 to the power d. Right? It was roughly like this. D by 2? Yeah, D by 2. Thank you. Yeah, D by 2. D by 2. So that something special happens when n is 2 to the power. Let's see.
Minus 2 by 2.
We're going to get this as n divided by 2 to the power d by 4 plus minus 2 to the power d by 4. Yeah, so that when n is equal to 2 to the power d, something good will happen. Okay. But the main idea was that, okay, by the way, in getting this formula, we assumed that there was an overall half, both for this graph and for this graph. Now, if you think about the logic for open strings, there was no half. Because the half was because we did half into 1 plus omega. So, logically speaking, there was no half for the open strings, but there soon will be, because we'll allow the open strings also to be unoriented. Okay, so it was a sort of backward logic. I put in that half, even though from what we'd said that needn't have been there, but in today's lectures it will be. Okay, so now what we have to do is to try to understand how open strings, okay, how open strings behave under orientation reversal. Okay, so let us remember what an open string was. It went from 0 to pi. And let's remember that we put, so far we've put Neumann boundary conditions at the end of the string. Okay, so we get Neumann boundary conditions tell us that the expansion of the string is in cos n sigma. Cos n pi sigma.
No, your sigma is from 0 to pi, then cos n sigma.
Thank you. Cos n sigma. So when sigma is 0, we always get it's like cos. When sigma is pi, it's also like cos around there. Right? It's like that. Okay, and then we have some e to the power I. Then we have the time dependence. Now, let's look at it in the following way. under orientation reversal, what happens? Under orientation reversal, okay, so we've got some business here, some alpha n, some time stuff, and cos n pi sigma, cos n sigma. Okay, now orientation reversal is what? It's effectively sigma goes to minus sigma. Or more precisely, just a minute, sigma goes to, is it like pi minus sigma?
Sigma goes to
Pi minus sigma, because the thing that starts here should actually start here. Okay, so we're interchanging, we're flipping this around. Okay, so sigma goes to pi minus sigma is the flip that we're talking about. Okay, so that this endpoint gets interchanged with this endpoint. Yeah, the problem with sigma goes to minus sigma is that it flips this. It takes the strip that was 0 to pi and makes it a strip that where sigma runs from minus pi to 0. So it's not going back to the same problem. Okay, whereas if we had sigma running from 0 to pi, and you do sigma goes to pi minus sigma, then this new sigma, sigma prime, which is equal to pi minus sigma, or sigma is equal to pi minus sigma prime also ranges from 0 to pi. So you're going back to the old problem. So that's a way of thinking of it formally. Logically, of course, you're just trying to switch these and put it back. Okay? So now let's see what happens to when you do. So we've got alpha n cos of n into pi minus sigma. Okay? Now, so let's suppose n was 1. Okay, so this is equal to alpha n cos of n pi minus n sigma. Okay?
minus 1 to the n.
Exactly. So suppose n was 1, this would be cos of pi minus sigma, which is minus of cos of sigma, because you know this is cos sigma, this is cos of pi minus sigma. But if you do n is 2, it's come back. N is 3, once again it's there. Okay? So cos of n pi minus n sigma is the same as minus 1 to the power n times cos of n sigma. Okay? So what we see from this is sort of interesting. The action of orientation on the oscillators of an open string is alpha n goes to minus 1 to the power n alpha n. Okay? That's how omega acts on the oscillators. But now, what? Exponential? Cos is this. Yes. Okay. Great. So far we've got the action on the oscillators. But remember, the open string, apart from having oscillators, has Chan-Paton factors. Okay. Apart from having oscillators, has Chan-Paton factors. And the Chan-Paton factors were I and j. Clearly under this flip, what you should expect is that I goes to j and j goes to I. Okay? Now, there is this long story here about whether you could allow more. Well, clearly what you're going to have is the left and the right getting interchanged. But there is this question about can we accompany this interchange with a similarity transform? Okay, so let me quickly go through this this analysis for you. I'll explain the issue. Yeah, let me find the right place in Polchinski. Where does Polchinski first talk about orientation? Well, that's useless, I'm sure. Just a minute. orient 4277. Just 1 minute, please. Unoriented. Unoriented string 189. Okay. Okay. So let's take a minute. So we've already figured out the action of the action of orientation on the oscillators. Now let's take a minute to figure out what the action on the what the action on the Chan-Paton factors might be. Okay, so what Pulchinski says is, well, clearly what's going to happen is that suppose I've got this lambda, which is the Chan-Paton matrix. Okay, so I have lambda ij as my state, summed over ij. Okay, Pulchinski asks, could you allow the action to be, clearly lambda has to go to lambda transpose because left and right have to interchange, but could you allow this to be accompanied by some sort of similarity to some basis transformation? Okay, so you ask, suppose we have gamma lambda gamma inverse. Okay, we have gamma lambda gamma inverse. Okay, is that a possibility? Okay, now look, suppose, you know, this is the kind of thing that we're doing here is to examine. It's like the issue with projective representations. Are you guys familiar with this? You know, in quantum mechanics, suppose you've got a symmetry operation. Okay, you've got a symmetry operation and you've got an operation acting on a state in the Hilbert space. Now, the symmetry operation we tend to say has to be implemented by operators that obey the Lie algebra, that obey the commutation rules or the group multiplication rule. But that's not strictly necessary, because you know, in quantum mechanics, two states that differ just by a phase actually represent the same physical system. So if the commutation relation or the group multiplication property is obeyed up to phase, physically that is implementing the same physical symmetry. Okay, so in quantum mechanics, the statement that a symmetry is implemented by operators that obey the symmetry algebra is not always correct. Okay, it can be that it implements it up to phase. These are called projective representations of the symmetry, and sometimes lead to interesting physics. For instance, SOD does not have spinorial representations, as you know, because 2 pi in SOD is identity, but on spinorial representations 2 pi doesn't act as identity, it acts as -1. But that's okay in quantum mechanics because -1 is a phase. Okay, and it turns out that there's this nice theorem, let's say for SO3, that all projective representations of SO3 are genuine representations of SU2. And that's why SU2 representations are okay in quantum mechanics, even though, you know, rotations are SO3, right? Okay, so this is the kind of thing that we're worrying about. We're worrying about whether this thing which is just going to flip left to right can do it in a way that is accompanied by a gauge transformation. That's what this gamma is. You get some rotation of the gauge indices. Okay, so that you don't tell the difference. You know, these are physically equivalent. This is the same kind of general question. Anyway, so we're going to ask, could it be that the transformation law is something more complicated? Now, something that we demand is that if you do orientation reversal and you do it again, you come back to the same thing. That's like a physical thing we require. So let's try to do that. What let's come back to the same thing. So we want gamma lambda transpose gamma inverse. When we transpose this and multiply that by gamma transpose, sorry, gamma inverse. Now what do we get? When we transpose, we get gamma inverse transpose lambda gamma transpose gamma inverse. Which is the same as
Gamma transpose.
yeah. So let's call this is gamma transpose gamma inverse transpose
Yes.
lambda gamma transpose gamma inverse.
No, okay, fine. If you take it to be A,
Yeah, I mean,
A transpose.
Yes.
Oh,
No, it's fine.
I mean invert.
Which one you are calling gamma is gamma prime.
no, but I shouldn't it be the same as this? That's what I was saying.
No, that should be an inverse on the last line.
On the last line, wait.
Yeah, that one.
That should be an inverse.
That should be an inverse.
Inverse. Thank you.
Yeah.
Thank you. Yeah, thank you. Because now that will become
Yes.
gamma
Yes.
and gamma transpose inverse.
Yes.
Yeah, thank you. Okay, now this has to be equal to lambda for all lambda.
Yeah.
The way, since lambda, there's no restriction on what lambda is, the only way this can work is if this gamma transpose gamma inverse is identity.
So gamma is
Okay.
symmetry.
Yeah, so gamma transpose, wait, it should be identity times a number. Because a number goes through everything. The number has to square to 1
Yeah.
because it should be equal to itself. So basically gamma transpose gamma inverse has to be equal to plus minus 1.
Yes. Yeah.
Why
Okay.
number have to be 1?
Why does the number have to be, it has to square to 1 because we want this guy to be equal to lambda. So suppose this was this, we'll get another thing from here, and that the square of that number has to be 1.
Even if this is A into some identity.
Yeah.
Because it's
Then
inverse,
also
you're saying.
for
Thank you,
the
thank you,
identity
thank you.
equal-
Thank you.
In fact, any complex number.
Thank you, you're right. This can be at the moment any number. Gamma trans, some alpha.
Any complex.
Any complex number, you're right, absolutely right. So now. Yeah. Oh. Wait.
Unless we are preserving the norm of lambda.
Just a minute. What's gamma transpose? Yeah, right. But let's look at this. Suppose gamma transpose is equal to alpha. This implies that gamma transpose is alpha times gamma.
And determinant.
Take determinant to take eigenvalues. Okay, so alpha has to be.
No, now the alpha has to
You
be
can't
1.
absorb alpha into gamma.
What?
You cannot absorb alpha into gamma by some.
Yeah, you cannot because both are.
It always cancels.
Exactly.
Yeah, I mean,
So this here,
Alpha is 1, not even plus minus.
well,
No,
minus
if you
1
take-
should
If you
be.
take the determinant on one side, let's say on the second line, gamma transpose is alpha gamma. You take determinant of both sides. Okay, actually depends on the
Well,
first dimension of
well-
alpha. So
Well, it's certainly possible to have symmetric matrices, and it's also possible to have antisymmetric matrices.
No, no. What I'm okay. So alpha will be e to the 2 pi I over n, where n is the dimension of gamma.
No, no, wait. This equation has solutions.
No, no. What? Yeah, this is obviously one of the solutions. What I mean to say is that if you started with gamma transpose equals alpha gamma and took the determinant on both sides, on one hand you would have, on both the sides you would have determinant of gamma, and what would be left is alpha to the n equals 1, where n is the dimension of these gamma matrices. So, I mean, the most general solution is alpha is e to the 2 pi I over n.
Alpha is e to the power 2 pi I over n. No, but there will be something wrong with that. Wait, just a minute. I think just these will be the solutions. Just a minute. For instance, if n was 3, you wouldn't allow minus.
Yeah. Okay.
Something's wrong with this, right? Wait, okay, let me give you a clear argument. Wait. So gamma transpose, yeah, clearly this has to be, as we said, this has to be, and this alpha has to square to 1, right? Because,
But square,
No.
pi square.
No.
oh no, because of the inverse. Yeah, sorry. Give me 1 second, let me see what Partition says. Okay, firstly, let's see if his condition is the same as ours. He got gamma inverse transpose, gamma inverse transpose, lambda. He got gamma inverse gamma transpose. Did I mess this up? This is okay, right? I messed up somewhere, please.
Your convention is gamma lambda equals gamma inverse, right?
Gamma, whatever, gamma inverse, yes.
But in the last line, the third line, you said inverse lambda gamma. But it doesn't. That's same.
Right. Here, did I do this right? It was gamma, lambda transpose, gamma inverse, and then I took the transpose of that.
Yes.
Gamma inverse transpose, gamma, and here gamma transpose from here, and gamma inverse. Okay. Gamma transpose. Just a minute. Yeah. Okay. Come. Why? Just.
In the inverse transformation, if the matrices were gamma transpose gamma on the last line, then it would be okay.
So far, I can't see anything wrong with this.
Yeah, I mean,
Let's just go with this. Yeah, what have we concluded? So what we need is that gamma transpose gamma inverse is equal to alpha identity. I think you're right about that. So gamma transpose is equal to alpha gamma. This is correct.
yeah.
Now, now the question is, how do you solve this equation? Is there some reason we need this to be real?
Is the first like in the sense that when we are doing the inverse transformation, I mean, okay, this is just ad hoc. Let me say the very opposite. But if during the inverse transformation we use the gammas oppositely, then we would get something like gamma transpose gamma instead of gamma transpose gamma inverse on the third line. Okay, this is purely ad hoc. I mean, just
I didn't understand. We have to use the rule and use it twice, right?
Yeah.
Just one. Why plus minus? Just once. How's it going to be? Okay, Upmanyu's argument was that determinant of gamma transpose, which was equal to alpha times to the n times determinant of gamma. And then assuming these determinants were non-zero, you cancel this, and Upmanyu's argument was alpha to the power n is equal to 1. Which looks good. Already this confuses me though, because what if n was equal to 3? Clearly it's possible to have, but antisymmetric matrices only exist when n is even.
Yes.
Okay, fine. Or when the determinant doesn't exist. There could be a 0 and an antisymmetric part. Okay, so Upmanyu's argument is a good argument provided n is provided the determinant is non-zero. And now we want to, okay, good. So we've already cut it down by using Upmanyu's nice argument. Now we want to know whether these other non-trivial phases are possible. So suppose n was 4. Could we have I? So let's look. Sorry. Let's. Is it possible to have alpha transpose is equal to I times alpha for some 4 cross 4 matrix? Now, the other thing about alpha transpose and alpha is that they have the same eigenvalues.
Yes.
So it would have
trace will be the same.
More generally, the eigenvalue equation, determinant of this is equal to 0 is the same as its transpose, right? Okay, so if the eigenvalues are equal, the only way this could work is if every time for every alpha that was an eigenvalue,
I lambda
is also an eigenvalue. I lambda is also an eigenvalue, and that would restrict this to matrices whose eigenvalues are the 4th roots of unity.
Exactly.
Okay, so we could have a matrix, and now is it possible? Is it possible to have such a matrix such that it's transpose? See, is there some reason we should just one minute more? Okay, let's move on. There is some reason why, I'm sorry, I have to figure it out. There's some reason why we are only interested in gamma is equal to plus minus gamma transpose. I'll figure it out for next class. Why the Upmanyu's complex roots are not there's something I'm missing. But for some reason, these are the only ones allowed. I'll try to tell you next class. Okay. Now, the next thing that we can ask is what happens. You see, this lambda itself changed under. You see, what was lambda? It was defined by this.
Yeah.
Okay. So lambda itself changed under a basis transformation. So suppose you had I is equal to u I prime. But this is, I prime.
Yeah.
Suppose you did this kind of basis transformation. Okay? So lambda will change by effectively lambda goes to u lambda u transpose. This u and this u may be transposes of each other.
Yes.
Okay. So now you can ask so now if that happens, how does gamma transpose? You see, our rule was that right. So what we had was, let's say that in the original basis we had lambda goes to gamma lambda transpose gamma inverse. That was our rule.
Yeah.
But lambda itself now has changed by this amount.
Yeah.
Okay? So let's say that the original lambda went transformed like this. The question we're asking is, how does the new lambda transform?
Yeah.
Okay? So I'll write original lambda in terms of new lambda.
Yes.
So u lambda u transpose. Is it inverse? Just a minute. Inverse. Now why inverse? Just a minute. Yeah, I'm sorry. We're often going to contract one end of this index with that index. So sorry. So I'm sorry for getting so many things wrong. But this change would have had to be this, because this index, what we often do is contract things. Like we take traces, right? For instance, an IS matrix, we had trace lambda 1, lambda 2, lambda 3, lambda 4, as you remember. But these were the lambdas. What that means is we're taking the index on this side and contracting it with the index on that side. So if this is not to change structure, then if one changes with the u, the other changes with the u inverse. Okay? So, but now this is on the other side, so that's probably a u inverse transpose, right? We want that, no, I think we want, because we want this, we just want this. Because we want this trace structure, just inverse. Because we want this trace structure to be unaffected. So we want u times u inverse. So so actually just u inverse. And this is the kind of structure we want. Okay, so now we've got this goes to gamma, and then we've got this horrible thing. So that's u inverse transpose lambda transpose u transpose gamma inverse. Okay, now we take this u inverse here. So that's lambda goes to u inverse gamma u inverse transpose lambda transpose u transpose gamma inverse and u. Okay, so this is the effective transformation rule that we've put here. Relabeling U inverse as V.
Effective transformation of gamma under
Exactly.
change of basis.
Gamma goes to V gamma V transpose, where V was U inverse. Okay, so the question of, now, suppose the original gamma, we had said that gamma was equal to plus minus gamma transpose.
Yeah.
This is going to preserve that, right? Because suppose gamma let's look at what happens when we take the transpose of this. This is gamma goes to V gamma V transpose. Okay, now suppose gamma transpose was plus minus gamma, then this transpose is also plus minus itself, right? Because we take V gamma V transpose and take its transpose, that will be equal to V gamma transpose V transpose, okay, which was equal to V plus, so we can take the plus minus out, that's the point, plus minus V gamma transpose V V gamma V transpose, which was the original quantity. So this quantity transposed is plus minus itself if gamma transpose was plus minus itself. Okay, so this change of basis preserves this property. Okay, so this is the kind of transformation by doing this change of basis. It's the kind of transformation by doing this change of basis that that retains retains this property. Okay, now we can ask. So suppose I have a matrix such that gamma transpose is equal to plus gamma to start with. Go on.
About this superuse argument, if you have gamma transpose equal to, if you apply transpose one more time, there will be gamma equal to alpha square, and that will just give you plus minus.
Beautiful, beautiful. How lovely. Yeah, there we go. Yeah, so we don't need the determinant. So very nice. So the argument was now, let's take transpose once again. Okay, so this is gamma transpose, which is just gamma, is equal to alpha gamma transpose. So that's gamma is equal to alpha gamma transpose.
Alpha squared plus transpose.
So alpha has to be its own inverse. So alpha has to be. Thank you. Oh, that was a beautiful argument. Okay. Okay, excellent. Excellent. Thank you. Okay, so where were we? So we've got gamma transpose is equal to plus minus gamma, and we've got the freedom to do this transformation. Gamma goes to V gamma gamma transpose. Now we can ask the following question. Suppose I gave you. Can you give me one example? Can you give me one example of these gamma matrices? Okay. Can you give me one example of a symmetric gamma matrix? Well, one very simple example of a symmetric gamma matrix is just gamma is equal to identity. Okay? And there is a theorem one can prove that if gamma is symmetric, gamma transpose is equal to gamma, then by doing such transformations, every such symmetric matrix
returns its symmetry.
Can be transformed into identity. Okay? Every symmetric matrix of the form, every symmetric matrix can be by such a transformation. Every symmetric matrix can be, by transformation, be put to gamma equals identity, which is another way of saying that every...
Diagonalizing and then rescaling the eigenvalue, I mean, also.
This is not, note this is not a similarity transform.
Yeah.
No, this is a theorem one has to prove. Actually, the way one proves it is to use the fact that a symmetric matrix can be written as unitary times diagonal. Diagonal times unitary, and to do some manipulations. Okay, but it's a theorem one can prove. We can take it as an exercise. Some simple manipulation with matrices. Okay? Basically, it's the statement that every symmetric matrix can be written on the form VV transpose.
Yes.
Right, because of this was identity.
Yeah.
Clearly, VV transpose is symmetric.
Yeah.
And the claim is that every symmetric matrix can be written in this form. This one you can try to prove. Okay? Similarly, there's a related statement about antisymmetric matrices. Every antisymmetric matrix can be written, every antisymmetric gamma can be written as V eta V transpose, where eta is equal to 0, 1, I minus I 0.
Symplectic.
Exactly, the symplectic metric,
Yeah.
the symplectic form.
Yeah.
Okay, Pulchinski likes to put an I and to make it a Hermitian matrix. Okay, this I will leave you to investigate why it's true. Okay, so we're going to do the basis change to make this transformation. So what have we got in the end? If gamma is identity, we've got nothing, right? Meaning, if we were very naive and we just said that under flip, lambda goes to lambda transpose.
For this matrix, what is the division? Like where 0 stops and 1?
It's equal. So this you can only have a matrix, antisymmetric matrix if your dimension is even. So the rank of the matrix, the size of the matrix is 2n, and then identity is n and n. See, an antisymmetric matrix has to have equal positive and negative eigenvalues. So this is like it's like.
I'm saying if this is the I index, then 1 to, let's say I runs from 1 to 10 or 20.
Yes. So the first 10 are here. This will be 10, 10, 10, 10. If the I index runs to 2m, it has to be 2m if it's antisymmetric and non-trivial. Okay. Then we don't want some zero eigenvalues here. Yeah, because that would basically say that under the transformation, one of the indices is removed, which will make no sense. Okay, so basically, what you're going to get is that the gamma is either identity, therefore lambda goes to lambda transpose, or gamma is the symplectic identity, which is lambda goes to this eta lambda transpose eta inverse. With this very particular symplectic form matrix. Okay, this is for lambda symmetric, and this is for gamma symmetric, and this is for gamma antisymmetric. Is this clear? Okay, excellent. So, this was the totally naive thing to do, and will turn out to be what's relevant anyway. Okay, so if you weren't as creative as Pulchinski was, or the people who Pulchinski was reporting were, you wouldn't have made a mistake here in the exercise we're going to do now. But there are situations where the second one arises. Okay, so it's good to keep it in mind. Okay, so these are the two possible transformations of Chan-Paton vectors. Okay, now that we have these, we can go ahead and compute this the analog of the cylinder diagram. Okay, and that's what I'm now going to do. Okay. Thanks to the clearing up, we have no loose ends, and we're good to go. Okay, so as usual what we wanted to do is to compute trace e to the power minus, now e to the power minus, now what did we call it? Did we call it e to the power minus 2 pi beta L0? What was our, oh, we just called it t, right? 2 pi, did we have a t? I'm sorry, when we computed the open string, what partition did we?
2 pi t.
Minus 2 pi t L0. Good. So we had, we want trace e to the power minus 2 pi t L0.
Yeah, L0 plus L, okay, yeah, L0 part, but.
L0 plus L0 bar, fine. Okay, we have this trace e to the power 2 pi t L0, L0 plus L0 bar.
Yeah.
Okay, but we have 1 plus omega by 2. Where this omega action now we understand. Okay, now the first part is what we've already computed. Right? The first part is what we've already computed. This is the thing that's going to give us the n square by 2. Because that's the one, it doesn't know that there's some orientation reversal going on. And that's why we divided the original diagram by 2. Okay? What remains to be computed is this guy. Okay? Let's first do the calculation for the case that gamma was identity. The simpler of the two cases. Okay? So now this is what? Let's look at, so we have to separate out this computation. So now what we're doing is computing this guy. This was that, this was the diagram we talked about, the Mobius, the diagram we talked about last time, right? Okay, so fine. First, what is the difference between this diagram and the diagram we got for the open strings? Well, there's the oscillator part and there's the Chan-Paton part. Those are separate Hilbert spaces. So we do the trace in each of these Hilbert spaces separately. Okay, let's first look at the Chan-Paton part. In the Chan-Paton part, we had Ij and Ij. This is the trace sum over Ij. It's doing this sum that gave us the n square in the term that was 1.
Yeah.
Because all values of I and all values of j, that gave us n square. But now, how does orientation act on this Ij? It just transposes, so it makes it ji. So what we have is sum over Ij and ji. Okay? But this is 0 unless I is equal to j.
Just n.
And therefore you get n. So from the Chan-Paton part, instead of getting n squares we got previously, what we get is n. Now let's look at the oscillators. Okay? So the oscillators, how do they go? Okay. The oscillators, if you remember what did we have last time? Just let's remember what it was for the ordinary open string. It was product n is equal to 1 to infinity, one of these for each oscillator, 1 over E1 minus e to the power 2 pi nt, and an extra factor of 2, right? Could somebody check? We got eta of 2t, right? 2it, right? let me just make sure that factor of 2's are correct. A cylinder. No, sorry. Right. Sorry, the factor of the 2it was in the oriented guy. The 2 was because we were setting left mover to be equal to the right mover. So we got twice the energy. This was just this. Effectively, it was exactly the spectrum of one left moving guy. Right? So this was, just no T. And in the case of the cylinder, this was just eta of it. And then the zero mode part and so on. All that is the same as for the cylinder. Okay? Oh, what is different here is that now, what is different? What is different is that the guys with odd n and the guys with even n behave differently. Why is that? It's because orientation reversal acted on the nth oscillator, picking up a factor of -1 to the power n. Okay? So the guys with even n, nothing has changed. But the guys with odd n, do you see that the sign becomes a plus? Because one oscillator gives you a minus sign, but two oscillators give you a plus sign. Right? So imagine taking this and doing a power series expansion. You want to multiply each occurrence of that oscillator by -1. So that changes the sign to -1. Is this clear?
Could you explain?
Sure. So let's take the oscillator n equals 1.
Yeah.
So I'm claiming the right factor for that is 1 plus e to the power 2 pi t. Why? Let's expand this out. What is this? It's 1 minus e to the power minus 2 pi t plus e to the power 2 pi t square minus e to the power 2 pi t. So all this minus 2 pi t cube and so on. But that's exactly what we wanted. Because how did orientation preserve? How did this omega act? What we did, what we had was, let's look at just the sector involving the oscillator with n equals 1. Okay, so let's say that the occupation number of that oscillator was n. Every oscillator creation operator, let's not call it m, let's call it m because n is 1. What is this? This is equal to alpha minus 1 to the power m acting on 0. Okay, so how does omega act on this? It acts on each of these with a minus sign, and therefore acts on this state with -1 to the power m.
Yeah.
Okay, now the trace we have is m omega m. Therefore, this omega on m gives us an extra factor of -1 to the power m. So the guy with mth occupation, m occupations of that oscillator comes with a -1 to the power m. Okay, but that's exactly achieved when we do this, right? Odd number gives a minus sign, even number gives a plus sign.
And we have to affect this there as well on the
Yeah,
top
so
line.
yeah, exactly. So that now makes this formula what?
Yeah, I mean, eta.
Product n is equal to 1 to infinity. Then so let's do it. Product m is equal to 1 to basically I'll just write it out instead of product.
Yeah.
I'll just write it out. It's 1 over 1 plus e to the power 2 pi t into 1 minus e to the power minus 4 pi t
Yeah.
into 1 plus e to the power 6 pi t
Yeah.
and so on. Minus 1 to the power n, you can do that, right? That's -1 to the power n. Exactly. Exactly. That's exactly right. Okay. All of the rest, the zero mode part, Everything else is totally unaffected. It's just as we did in the computation of the open string. Okay? Yeah. Now, so we have the answer. So let me just, maybe I'll just write down the answer just to be totally clear.
Yeah, it will be some eta some complex t plus I phi. Because that minus 1 to the n we can write as e to the I n pi, and that will be
Very good.
pi n t plus I n pi. So eta of this complex argument.
Yeah, that might be a way of deriving what I'm going to say next. That's well said, yes. So Upmanyu's point is that this is same as eta of this thing was eta of it,
Yeah.
but you just shift t by I by 2.
I pi over 2.
I by 2, right?
I by 2.
Yeah.
Yeah. I n by 2.
N is automatic.
Yeah, right. Sorry. Yes. I by 2. Yes.
Yeah. So Upmanyu's point is that this is the same thing as eta of I into
I t plus half.
t plus I by 2.
Yeah.
I by 2. Yeah, that's nice. That's nice. That's okay. Now so let me just write down the answer. Let me write down the answer completely. Okay. So just for normalization, cylinder was equal to some stuff we're not keeping track of, some number, overall volume and so on, n square by 2 dt by 2t, and again 1 by t to the power d by 2, eta of 1 by eta of it to the power d minus 2. We're assuming the ghosts have been taken out. That's why the d minus 2. Okay. With that same normalization, the Mobius strip, this thing with the omega. Okay. That would basically be this modified eta. Nothing has changed except the n. So there's n. There's this by 2 dt by 2t 1 over t to the power d by 2, and then Upmanyu's 1 over eta of it plus I by 2. This modified product. This modified product to the power d minus 2. Oh, now one should be a bit careful though about this.
Yeah, I mean this can be taken minus I over 2 as well, or
No, because we don't want to do the shift in the 0 point. Eta includes 0 point. We should be a bit careful. Let me just keep 0 point times this. Okay, I won't be so sophisticated. Okay, okay. In fact, sort of luckily mathematicians have a name for this. Precisely this function, you know.
oh, Jacobi.
Yeah. It's theta 0, 0. It's called.
This, with 2 arguments.
Exactly. dt by, yeah, perfect. These guys, they call this guy, in fact they call the square of this guy. So they call this square root of, so theta 0, 0 it to the power d minus 2 by 2. This stuff together with the 0 point stuff oscillate up together with 0 point as a name, a mathematical name. Okay, and more particularly, square as a mathematical name. That's why this square root. Okay, some name. Okay, So let me just check the normalizations. There's the 4 here, the 4 here, d to the power d by 2. Yeah, all that has changed that this has become this and this n squared has become a. Okay, all good? Okay. Now, yeah, that's perfect. Now the thing is to move to the S variable. Right? So what we want, just like what did we do here? Here we did the variable change, t is equal to 1 by s.
Yeah.
Okay? And we were helped by the fact that we knew what eta of 1 by s was, or of I by s was. It was eta of I times s. Anyway, we're just going to do the variable change here. And then we will use an identity given to us by the mathematicians. Okay, we'll use an identity given to us by the mathematicians for that modular transform.
Abstruse identity.
No, it's a simpler thing. Abstruse identity is complicated. This is just modular transformation. You know, the reasons mathematicians are interested in these functions is that they have good properties under modular transforms. That's why they've defined all of these things. So they know how these things transform under modular transforms. I personally have never proved this identity, but I have no doubt that if we sat and did it, it would be a fast thing. Maybe using basically Upmanyu's idea and keeping track of the 0 point stuff. So separate out the 0 point stuff. Then Upmanyu got it right? Then put that 0 point stuff back, play around. I'm sure it'll be easy to do. I haven't ever tried it, but first let's write it out and then we'll try it. Okay, so okay, now first we'll write it out. We'll write this out as we just do the change of variables. So this becomes n by 2 ds by s. Then this guy goes, everything goes away. No ds also. So this of course becomes s to the power d by 2. No, s to the power d by 2 minus 1. Minus 1. And divided by theta 0, 0 of I by s to the power d by 2 by 2. Okay. So now we need to know what this quantity is from the mathematicians. Okay. Last time we knew just because we knew how etas transform, and we knew how etas transform because we did it using path integrals, right? I haven't tried to find a similar derivation for this, but Pulchinski claims this quantity is what? Is this 2 to the 13? This quantity is something complicated. Let's see. Let's work it out. So he claims that this is the same as ds. Then 2 I'll get the factors 2 right, just 1 second. ds theta 0, 0 of 1 by theta 0, 0 of is to the power d minus 2 by 2. But we also get an eta of 2is by and his minus 2. Wait. I'm sorry. This was theta 0, 0. There were two arguments here, 0 and 2it. The 0 remains, okay. 0 and 2is by pi to the power d minus 2 by 2. And this is eta of 2is by pi. Sorry about all of this. Okay, and then I need to give you the right factors of 2. Just a minute. B26 n squared by 2 pi. Right. So in the normalization in which this was 1, was this n squared by 2, this of course has a 2n times 2 to the power d by 2. That's the claim. Just make sure I'm not missing something. This 4 pi. Sorry, there's a 4 pi m. Just 1 second, please. Pi, that must be a typo, right? I think this must be right. There's some 4 pi I can't understand. It must just be a typo. Okay, fine. Now the point is this. This theta 0, we know what it is. Okay, we know what the theta 0 is because that was just this quantity. This quantity is a formal power series product, but if we are going to evaluate it at s is equal to infinity, then we just take the lowest term in this power series product. So it's some very simple thing, right? It's just basically 1. Okay. Similarly, we know what the eta is. So because s is very large, okay. So we just take this formula or the right version of it. Once you have the modular transform, you just evaluate this. Okay. So this becomes integral ds times 2n times something. Okay. And the important point here is that that times something, of course, is 2 to the power. That's 2 to the power d by 2. That's from here. But then that something also comes with a sign that is minus. Why does this happen? You remember that basically we got this mode, this divergence from the closed string exchange. Closed string exchange was oscillator number -1, oscillator number 1. Oscillator number 1 contributing from here contributed with a minus sign. That was this business.
Yeah.
That was the -1 to the power n. So you know when you add in the part that contributes at level 0, at energy 0, the massless mode, that contributes with a -1, simply because the oscillator that is contributing to that guy comes with a -1. Okay, the tachyon would contribute to the +1, but that's projected out. That's what the GSO projection does. That's what the stuff does with the fermions. Okay, so the only thing that actually contributes here comes with a minus sign. This minus sign has its origin in the -1 from this guy. Okay. So now we're in business. If you buy this, I'm sorry I did this so schematically, but this is just mathematics after this. Okay, it's just mathematics of modular functions. We can try to find a physics proof of it if you want, but it's a simple thing. Okay, and there was this factor of 2. Yeah. So now let's see what we had before. We had n square and then the this guy n square times divided by 2 to the power d by 2, and then we had 2 to the power d by 2. This is an extra factor of 2 to the power d by 2 relative to the n square. So the 2 to the power d by 2 is not there, and it comes to the minus 2n plus this. Okay, and therefore that's n by 2 to the power d by 4 minus 2 to the power d by 4, the whole thing square. Okay, and therefore is equal to 0 if n is equal to 2 to the power d by 2. Okay. 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 Now, let's quickly also go through what would have. Okay, is this clear? Okay. So what we have checked here is that if we look at this dilaton tadpole condition, there are 3 contributions. There's a contribution from the n square part, the cylinder diagram. There's a contribution from the Mobius strip diagram, and there's a contribution from the Klein bottle diagram. This was the cylinder, this was the Mobius strip, this was the Klein bottle. They're different contributions, but if n is equal to 2 to the power d by 2, they completely cancel each other. Okay? Now, very quickly let's ask what would happen if we were right. Now, very quickly let's ask what would happen if we were in the other case. Okay, namely if gamma was, instead of being identity, it's not equal to identity, but was instead this symplectic matrix I 0 0. Okay, so okay.
Minus I.
What? Sorry?
One of the antisymmetric. The
Uh,
lower one is minus I.
the lower one is minus I. Thank you. Yes, exactly. Okay. So on the oscillators, of course, nothing has changed. This is purely now how things have changed. I mean, the only way things have changed is that they've changed on the when acting on the Chan-Paton indices. Okay. So let's to understand this, let's take the particular. Let's first take the particular case of 2, if it's a 2-dimensional thing. Okay. So gamma now. So what's the action on lambda? So what's the action on ij, for instance? Ij goes to gamma ij gamma inverse gamma ij gamma inverse transpose, you say? No, gamma inverse, right?
No, not gamma. It is V.
Sorry. The gamma is this.
Okay, sorry.
This is eta. I had called it eta. Clear? Eta is this matrix. Eta was the special value of gamma that we could always basis change our thing to. Okay, so last time what did we do? Last time we said, well, we had ij and then omega ij, and then omega just did the flip. Lambda transpose. Just a minute. No, I mean, didn't our lambda go to?
ij can go to either ij transpose or eta ij transpose eta. That's what.
Eta, exactly. Eta ij transpose. Yeah, exactly. Sorry. You mean ji? Thank you. Ji. Yes. Right. Exactly. So transpose that. Perfect. Okay. So now what we last time what happened was that all that happened was that we had this eta ij, okay, and then that flipped to ji, and then we used that what we wanted to do was compute the trace. Okay, so I had to be equal to j. Okay, now let's do the same thing. Okay, so what we've got is ij, then we get I prime j prime. We get ji and ji, and we have gamma. No. We have gamma I alpha just a minute, sorry. What we have to do is to take ij and then on that do the transpose and multiply by on that do the transpose and then multiply by these things, right? Yeah. So gamma j alpha, alpha beta, gamma beta I with an inverse. Gamma is eta j alpha, eta inverse j beta. Is this good? Okay. Now how does this work? Now, the way this works is this inner product here is only non-zero if alpha is equal to I and j is equal to beta.
Yeah. So we hit with delta.
Exactly. So this, and then when that happens, these are 1.
Yeah.
So this becomes I,
Yeah.
and this becomes j. Okay. So what we get is eta ji, eta ij.
Yeah. Trace of.
So it's
I square.
It's trace
of eta square.
of eta square.
Yeah.
But eta square is minus 1.
Eta square looks like 1
Minus 1.
No, minus 1. Yeah.
Okay. So eta square is minus 1. And therefore, this quantity, instead of being n, as before, goes to minus n.
No, I mean, eta is something like the sigma 2 matrix. I mean, let's say in 2 dimensions. So eta square should be 1.
Ah.
I is
Oh, what about the I? Yes. Wait.
Yeah, I mean, including the I, it's like sigma
Yeah, but that okay, give me a minute.
Yeah, I mean, I don't see why.
But you have an, see, there's this eta
okay,
inverse, right? Yeah.
Yeah.
So, sorry, so this really was eta.
Eta.
Okay, so from this way of saying it, it just came directly from the I square.
Yeah.
Because eta times eta inverse,
Yes.
without the i's was just identity,
Yeah.
and then the I square gives you -1.
Yeah.
If you hadn't put the I in the eta inverse,
No, I mean, eta
No.
and eta inverse, they
it's,
go away.
it goes away, exactly.
Yeah.
So if you had defined it without this, you would have still got the answer -1. There the answer would not have come from the i's, but in whatever. Okay, so so the answer here is -n. So what would have changed here? It's just that this -n would in this case have had two minus sign contributions. One from the fact that the -1 oscillator went to minus, and one from this additional minus sign from the funny symplectic metric. Okay? So this in this case would have become n square plus 2n, n squared divided by d by 2 plus 2n plus 2 to the power, n squared divided by 2 to the power d by 2 plus 2n plus 2 to the power d by 2. Okay? That doesn't work for our current purposes. There will be things for which we will need this plus as we proceed later on. But for our current purposes, it doesn't work. Okay? So the only option that works for us is this eta equals identity, and n is equal to
8192 in bosonic string theory.
exactly 32 for the superstring, and this 8192 whatever for the bosonic string. Now, okay. One thing we have not carefully kept track of is though I kept this d by 2, I actually did the calculation for the bosonic string because I was never very careful about what happened to the fermionic part. I'm going to leave the following as an exercise to you. The fermions change nothing. It's really all the d dependence comes from the bosons. Why is that? The reason for this is basically the following. In doing the calculation, what we had to do was this modular transformation on the partition function. So let's imagine, for instance, just for the cylinder guy, we had to do the modular transformation on the partition function. Now, the fermion part of the of the partition function was just genuinely the oscillator part. Fermion oscillator part of the partition function was genuinely modular invariant by itself. In the bosonic part, that didn't quite work. You required messing around with the t to the power d by 2's. Do you remember? This was the big difference between the cylinder partition function and the torus partition function. That is, the torus partition function was modular invariant by itself for the bosons. But the cylinder partition function for the bosons was not quite modular invariant, because the oscillator part got square rooted, but the zero mod part did not. And therefore what happened was that the zero mod part, that 1 over t to the power d by 2, was absorbed away when doing that modular transformation. Modular transformation is just this t goes to 1 by t goes to s. Okay? However, the oscillator part of the fermionic partition function is just by itself modular invariant. So that part just, all you have to do is do everything we've done in class, but do the modular transformation also on the fermionic part. But that part is almost trivial because it's by itself modular invariant. Okay? The interesting thing from the bosons was that it ate up that extra factor of t to the power whatever. Okay? There was no analogous thing for the fermions. If you remember, for instance, when we started studying the superstring, what we did was to look for modular invariant fermionic partition functions. They were nice and modular invariant. Basically, the reason that the fermions worked so much nicer than the bosons is that the bosons have a non-compact zero mode, where the fermions do not. The fermions have a zero mode, we just get zero, right? Like the Ramon sect. It's a fermionic zero mode. Okay? So if you just, in your mind or on paper, go through this calculation in the superstring, just taking the fermions and putting it on the right, they just go along for the ride, and in fact were necessary for all our conclusions, because they were the things imposing the GSO projection, telling you that that S thing is just the partition function, where the lowest thing that runs is the closed thing. Okay, I'll leave that for you as an exercise. It's basically nothing has changed. But just convince yourself that all the arguments that we've gone through go through also with the fermions. Nothing has really changed. They play the role of a spectator, just giving the right, GSO projection. That's all. There's no mixing with the t to the power, which gave us all the fun. Because remember, it's the integral over S that gave us the divergence. The integral over the S was the integral over t. That was all from the zero mode sector. Okay? Is this clear? Any questions or comments about anything we've discussed? Any questions or comments about anything we've discussed? This theory, the theory where we take, I should have said, in the case of the bosonic string, when we did the orientation preservation, we modded out by omega. We of course did it because it was we could do it because it was a symmetry of the world sheet action. Parity was a symmetry of the world sheet action. Parity is also a symmetry of the world sheet action for the superstring, because we have one left moving fermion, one right moving fermion, just like we had, okay, the two fermions, Dirac fermions are just parity invariant, right? However, in defining the superstring, we had more than the world sheet action. We also had a GSO projection. And remember that in type 2a theory, okay, in type 2a theory, we had one sign in the, do you remember the partition function? There was this, plus this, plus this, plus minus this. And we put one sign for the left movers and the other sign for the right movers. So type 2a theory cannot be modded out by omega. Right, type 2a theory cannot be modded out by omega, because the type 2a theory cannot be modded out by omega because you cannot simultaneously impose gauging by orientation as well as the GSO projection that defines the type 2a theory. Okay? So this orientation gauging can only be done in the type 2b theory. Okay? So the type 2b theory with which has been gauged out by this omega operation has a name. It's called type 1 theory. Okay, so this is an interesting theory. This is an interesting theory because now it's a theory, it's a consistent theory of closed strings and open strings. Okay, and it's a consistent theory of closed strings and open strings. And very quickly we're going to ask the following question. In this theory, the open strings give rise to gauge bosons, as always. And I want to ask the question, what can we say about the gauge group? Okay, in which these gauge bosons transform. Okay, now let us remember what the vertex operators for the gauge bosons were. the vertex operators for the gauge bosons were alpha to the power minus 1 times ij. For just a general open string, it was alpha to the power minus 1 times ij. Alpha to the power minus 1 times ij, where these ij's here were arbitrary. I was anything, j was anything. Okay? But now let's look at what happens under orientation preservation. Okay, the orientation operation takes, so suppose I have this by some lambda. Okay, so there's alpha to the power minus 1 and then some ij that I'm denoting by some lambda. Okay, so under the orientation operation, the parity operation, this state goes to minus itself times lambda transpose. Okay, so the same minus alpha minus 1 times lambda transpose. Now, which of these states then survive? Which of these states are invariant under orientation preservation? Those states such that alpha minus 1 lambda is equal to alpha minus 1 into minus lambda transpose. Okay, so those are the states such that lambda is equal to minus lambda transpose.
Yes, sir.
Exactly. This is the condition for the Lie algebra of SO. SO what?
Yeah, as many dimensions as
SO 2 to the power d by 2. Is this clear? Okay. So, right. So in this theory, what we have in this type, for instance, in type 1 theory, what we have is a theory of open strings interacting with closed strings, and the gauge group associated with the open strings is SO32. Because n is 2 to the power d by 2. So each of these, this is an n cross n matrix. And n runs from, is a 32 x 32 matrix such that lambda is minus lambda transpose. So it's an SO32 adjoint matrix. Okay, and one can check by direct computation that the gluon scattering at low energies is reproduced by Yang-Mills, the Yang-Mills action for SO32. The same kind of calculations we did. One can redo. Okay, so this is a sort of interesting theory, but we're already getting hints of something something sort of nice. Where else have we encountered the gauge group SO32?
Heterotic strings.
Heterotic string. Okay, so there's another SO32. These are very different looking theories. For instance, the type 1 theory has no B mu field, if you remember.
yeah, projected out by
Because it's projected out by the orientation preservation. Because in the closed string sector, it's just alpha minus 1 goes to alpha minus 1 tilde. But B mu has had that antisymmetric. So that was projected out. It had the graviton, everything has the graviton. Okay, but it had no B mu. On the other hand, the heterotic thing certainly has the B mu. Now, in this type 1 theory, maybe we should do a little bit more of that. Maybe I'll do that next class. I will, for each of the 10 superstrings, I'll go through the massless sector and the charges of the theories a little more systematically than we've done so far. I'll do a bit of that next class. But in the type 1 theory, what you see is that there is another two-form field which comes from the Ramond-Ramond sector. Do you remember, this we'll go through in detail next class. But do you remember the Ramond-Ramond sector? You see, the Ramond sector was a spinor. The Ramond sector, therefore, is a product of two spinors. But all of you know that if you take the product of two spinors and you expand it in group theory, what representations you get? You get forms. Now, depending on where the chiralities of the two spinors, If you do chiral with chiral, you get either even or odd forms depending on dimension. If you do chiral with anti-chiral, you get the other one. Okay, so if you would do this exercise for the particles, we'll do this next class. But in this case, the fields of the theory in the Ramond sector transform in even forms. So you get a scalar, which is sometimes called the axion. You get a 2 form, then you get a 4 form. Now, each of these have an associated field strength. The field strength associated with this is 3 form, the field strength associated with this 5 form, and so on. Now, every time you've got a 2 form potential, it would be very strange if, and this 2 form of course comes with an associated gauge invariance. Okay. Every time you've got a 2 form potential with associated gauge invariance, it would be very strange if there was no object that was charged under it. And in this case, there are objects that are charged under it. This is, we're going to go ahead, we're going to study it starting next class. These objects are called D1 branes. Exactly. Exactly. These are solitonic objects that are string-like. So, this is a theory with no fundamental strings, but D1 strings. On the other hand, the heterotic theory is a theory.
It is fundamental strings which are not under the Ramond, but which have the Ramond charges.
This one, yes. Yeah. This is these D1 branes have charges under the Ramond fields, but have no charge under B mu nu, which is good because B mu nu in this theory doesn't even exist. Okay. On the other hand, in the heterotic theory, there's B mu nu, there are fundamental strings. If you take the heterotic string theory and put it on a circle, okay, then the fundamental strings can wrap around the circle there. That gives you a conserved charge. If you take this theory and put it around the circle, these D1 strings can wrap around the circle. That gives you a conserved charge. Both of them can have SO32 gauge group. What is the relationship between the two? We will see that there's fabulous evidence that these two theories are strongly coupled dual to each other. That you take this theory at strong coupling, it becomes the heterotic string at weak coupling. And you take the heterotic string at strong coupling, it becomes this theory at weak coupling. Okay? So we will discuss all of this as we go along. Okay? There is this broad structure of string theory which okay, but for now let's be content with the fact that we have at least encountered all the 5 well-known 10-dimensional perturbative string theories. What are they? It's type 2A theory, it's type 2B theory, there's the heterotic SO32, there's the heterotic E8 cross E8, and there's this type 1 theory. Okay? So now you know what each of these theories are, and if you think about it, you know the rules for computing perturbative string amplitudes in all of these theories. You may have to look up chapter 12 in Polchinski to actually do it. But you know the rules. Okay? So in the next class we will continue to discuss toroidal compactifications of string theories and D-branes, and maybe I will take a little interlude to tell you about the maybe we should have a little class describing the maybe before that we should have a little class describing the massless sector of the 10 of these 10 dimensions. I'll give you a little rough introduction to the physics of these 10 dimensional theories, and then we'll go on to describe toroidal compactification. Now this Thursday